In this video, I'll be talking about the Doppler speed and distance logs that are used on ships to measure speed and distance. Now, in my previous video, I talked about the electromagnetic speed and distance log, but this video will focus only on the Doppler speed and distance log. But I'll provide you with a link on my previous video on electromagnetic logs along with this video as well. Alright, so the Doppler log is actually one of the most common and popular modern ship's logs, which uses the Doppler principle to measure the ship's speed. It uses the sound energy or the acoustic energy as a signal, but unlike the echo sounder, this device does not need a timing device. It is claimed to be more accurate than the other type of logs and is particularly useful because in shallow water it can measure speed over the ground, in deep water it can measure speed through the water, and in medium to shallow depths it can measure either speed over the ground or speed through the water. If you fit a transverse axis beam to the Doppler log, it can also measure speed sideways, which is very useful when berthing especially large ships. Alright, so before we go into the Doppler log, we must understand the principle of this log, and we must familiarize ourselves with the Doppler effect or the Doppler shift. So the effect of the Doppler principle is best shown by this example here. So imagine the pitch or the note of the whistle of a train which is coming towards you is higher than when the train is going away from you. Am I right? So as the train passes you, the whistle note will, or the sound of the whistle drops from higher to lower, and the note heard by the listener is higher than transmitted from an approaching sound source, and it is lower than transmitted from a receding sound source. The same effect is heard with a fire engine or ambulance sirens. So if you pitch, if you didn't understand what I mean, I'll show you in the next here. So just when I play these sounds, just focus on how when the sound is far away from you and when the sound is nearing you, how the sound changes in frequency. So when the sound is far away from you, it will of course be, the frequency will be different from when the sound is near you, and then when the sound passes you and goes away again, the frequency. So this was the sound of a jet plane, and say for example an ambulance siren is coming towards you and then passes you and goes away again. Just notice a change in the frequency. Alright, so now if the pitch or the frequency of the signal is graphed against the time, the following curve which you see in the picture here may be found. Alright, so for an approaching vessel and then the vessel that is going away, you can see the change in the frequency of the pitch. Now the difference between the frequency heard or measured by the listener and the frequency transmitted by the source is an indication of the speed of the sound source. So in other words, frequency difference depends on the speed. This is the Doppler effect, and the difference between the frequencies is termed as the Doppler shift. If the frequency difference can be accurately measured, then the speed of the vehicle can be found. Alright? And no timing is required, of course. So this is what we talked about before. Now if you talk about the Doppler log principle on which the ship's log is made, the principle is applied to the ship's log in the following way. Alright? So a beam of sound energy or acoustic energy is transmitted from the ship at a certain frequency. The energy is reflected from the seabed or the water layer, as you will see later, and returns to the ship where it is detected and its frequency measured for comparison with the transmitted frequency. So this is frequency transmitted, Ft, and Fr is the received frequency. When comparing both the transmitted and the received frequency, the following can be inferred. If the frequency received is the same as the frequency transmitted, the ship must be stopped. If the frequency received is greater than the frequency transmitted, the ship must be moving ahead. And if the frequency received is less than the frequency transmitted, that the ship must be going astern. Or something like this here. Let me show you through animations what I mean in each case. In this case here, the ship is stopped because the frequency transmitted equals to the frequency received. So this is the frequency transmitted and this is the frequency received. In the second case, when the ship is moving ahead, the frequency received is greater than the frequency transmitted. And in the third case, when the ship is moving astern, the frequency transmitted is greater than the frequency received. Alright, so this is the principle of the Doppler log. Now in the Doppler log, we have something called the Janus configuration. The Janus configuration refers to normally two beams which are used, one pointing forward and one aft, to eliminate some of the errors which exist within this log due to the pitching of the vessel. Alright, so this arrangement is called Janus. Actually, Janus configuration is named after, I think, a Greek god who had two heads, one facing forward and one facing aft, or one facing behind. So that's who after the configuration is named, if I'm not wrong. Alright, so the angle of the beam of the two rays is about 60 degrees to the horizontal and not directly perpendicular. The reason for this configuration is if it were less than 60, as you will see here, there would be too little reflected energy for the receiver. Alright, and if it is more than 60, there would not be big enough forward component of the beam to get a reliable speed measurement. Alright. Then there is another configuration called the cross-track configuration, in which an athwart-ship beam may also be provided on some systems, especially on vessels of more than 50,000 gross tonnage, which enables sideways or cross-track speed to be measured. So here you have two mutually perpendicular Janus configuration arrangements to measure the speed in two dimensions. This arrangement is also known as the docking log and provides the actual movement indication of the vessel. Now this cross-track speed may be permanently shown on an additional digital display, or it may be shown only when the cross-track button on the log is pressed, depending on, of course, your display design. The cross-track arrangement or the cross-track speed is particularly useful when it allows the integration of two separate speed vectors to get a much more accurate measurement of the ship's movement. Knowledge of this movement is particularly important and useful in general navigation, especially with sophisticated navigation computers which control course keeping very accurately to minimize steaming distance, time and fuel. Particular navigation as practiced by surveyors, exploration, seismic vessels, rig tenders and dynamically positioned vessels. It's also useful for pilotage when in strong currents and when berthing, particularly very large vessels, especially of more than 50,000 gross tonnage. Alright. Now in the Doppler log, there are two operating modes. One is called the bottom track and one is called the water track. Now this is the arrangements which are capable of providing speed through the water and speed over the ground. Now in bottom track, in shallow water, the energy is reflected off the seabed and thus the speed measured is speed over ground. This type of operation is called bottom track or bottom lock. In water track, it happens in deep water where the bottom is too far away to reflect sufficient energy of the sound waves. Electronic circuits within the receiver enable the sound energy reflection from a predetermined water layer to be used to measure the speed. The speed measured is speed through the water. And this mode of operation is called water track or water lock. If speed measured in bottom track differs from the speed measured in water track during that time, then definitely there is a current that exists. A log may be able to hold a bottom log down to about 200 meters. It might use a water reference layer at about 20 meters or 30 meters for water track. This log may operate at minimum underkeel depth of about 2 meters. Thus for underkeel depths of from 2 to 30 meters, the log must be operating in bottom track using reflections from the bottom. In depths greater than 200 meters, the log must be operating in water track only using the 20 to 30 meter reference layer. But for depths between 30 meter and 200 meters, the log can operate in either mode. The choice is, of course, of the user. The navigator selects which mode to use, except that the log will automatically switch to bottom track in shallow depths and to water tracking deep water. The log will indicate speed ahead or astern, whether presently in the bottom track or water track mode, and distance run. Alright, now like any other instrument, dependent on signal transmission and reception, the Doppler log also has some errors and limitations that you must be aware of. The first is the transducer alignment. The acoustic energy beams should be exactly fore and aft, as also the port and starboard beams. Most of the transducers have an indicating arrow, which is to be lined up with the vessel's forward and aft center line at the bottom of the hull. There have been cases where the transducers were fitted in reverse after a stay in dry dock, and as a consequence, the forward movement was indicating by a negative number or the stern speed and vice versa. Trim will also cause a misalignment of the beam in the vertical plane. But these errors are generally small, as the integrity monitoring done by using the Janus configuration mitigates the effect. Ship motions cause the next source of error. So rolling, pitching, surging and heaving all contribute to this instantaneous acceleration and therefore changes in speed which the log is measuring. This may then differ from the true forward speed of the ship. For a fore and aft axis log, pitch is the most significant cause of error. For a cross-track log, errors caused by roll can be significant. So errors caused by rolling can be significant. You as a user must pay particular attention to the instantaneous motions while relying on the speed shown by the log and must treat the readings with caution even after averaging them over a period of time. The final source of error is the sound and speed variation. So the speed of sound varies with water temperature, salinity and pressure. Temperature is the most significant of these. The log will read wrongly if the actual values differ from the assumed values. So if the temperatures are very high in warm water, the log may show different readings. Some Doppler logs may be compensated for errors caused by sea temperature change. Finally, the advantages of Doppler logs: they are very reliable and accurate. They can compute speeds both forward and aft and athwartship. They can compute cross-track speeds as well, and they can measure speed through the water as well as speed over the ground, which is not the case with electronic logs. Electronic magnetic logs can only measure speed through the water. The disadvantages is the officer on watch must pay attention to relative motion calculations if attempting to calculate the vessel's speed or current whilst water tracking. Alright, so I hope this was a quick lecture on Doppler log and it helped you to understand the principle of this log and how it works. If you have any questions, please feel free to write to me. I appreciate everybody who watches it and provides me with the feedback. I'll see you soon with my next video. Bye.